Okay, so welcome back. So in this video, we are going to look at what is called diffusion filtering. Okay. So far we looked at this best option that we have. That's a median filter. So what it does is it does a good job of preserving edges, but sometimes it may also alter edges because it does preserve edges only if edges are present at a certain orientation. They are straight lines, and it also depends on the intensity values. Okay. So diffusion filtering is an alternative to median filtering or other filtering approaches, wherein we can prevent edges from disappearing, and we can also allow for some smoothing near the edges. Okay. So diffusion filtering comes under the purview of the PDE based methods, so called. Sorry, move this. So it's one of those PDE based methods in image processing. Okay. We'll look at this topic later in more detail. I'll try to cover this also at that time. But right now it's good to have an introduction to the whole thing. Okay. So the way it works is, it treats the denoising process like a diffusion process. So basically what it means is that it treats the intensity as density, right? So if you look at diffusion, you think of material flowing from regions of high concentration to that of low concentration. So if you think of an image, right, you have noise in the image. Noise is basically some region or some bunch of pixels with abnormally high densities, right? So you would expect that if you can diffuse those high intensities out, that will be the equivalent of denoising. Another aspect of this process is that we would like to do this diffusion of these abnormally high values, but we don't want to do this across edges. So we want to preserve edges while doing this. Okay. So one way to know where we are at the edge, right? Because we don't know where the edges are beforehand. So there must be some way of figuring out where the edges are. So there could be abnormally high values near the edges also. But then the gradient directions are along or similar. So we can actually restrict this diffusion process near the boundaries and have it go on away from the boundaries or in regions of in nearly homogeneous regions in the image. Okay. Now if we assume that that if we don't distinguish between edge and non-edge pixels through some means, then this diffusion, if it carried out, is the equivalent of a Gaussian filter. Okay, this corresponds to what you can call a constant diffusion coefficient. Okay, inhomogeneous and anisotropic diffusion, the filtering prevents smoothing across edges to varying degrees, right? So anisotropic diffusion allows for the smoothing along a boundary but not perpendicular to it. Okay, so it makes use of the gradient direction. So we know the direction of the gradient at the boundary. Remember, the gradient is a vector. We saw that as two components. So you can figure out the direction of the gradient at every point. So you figure out where which is the tangent to the boundary and which is the normal to the boundary, and you only allow for diffusion along the boundaries. So that way you don't do the diffusion across the boundary. So inhomogeneous diffusion does not care about this direction, but it does treat the boundary like some kind of a semi-permeable thing. So basically the degree of smoothing is lower across boundaries when you are doing diffusion filtering. Okay. So let's look at the formulation of this. So this is formulated in terms of diffusion equation starting from a fixed law of diffusion, where the flux J is given by the following equation: minus D times gradient of U. Okay. So which is, just to make sure that we understand, dx comma y multiplied by this u, the gradient of u is nothing but f. Okay, so we'll see where that f comes from, and f is nothing but the image, but then represented in the continuous domain. We can of course discretize all of this, which is how it's typically solved. Okay, so this is the gradient, as two components, right? So the u is basically at time t equal. So this, at some point, we'll also see that that this is actually stepped across in time. So u is nothing but u at time t equal to 0. At this point, I'll just say it is just your input image, which we actually represent by f of x. Okay. So, see the type of diffusion that we talked about, right, where inhomogeneous or anisotropic diffusion is described by this diffusion coefficient. Now, this is what is called a tensor. It has multiple components. You can have, so a diffusion tensor can have multiple components or multiple elements in the matrix that specifies it. Okay. So what it does is it tells you for a given gradient u, density gradient u. This is basically, remember, this is the image at some time. What are the different directions, and how much diffusion is allowed across different directions. So that's what this D specifies. Okay, it tells you whether smoothing, the degree of smoothing allowed in different directions. So basically, what eventually happens is that's very similar to what we call this boxcar averaging filter. There is some averaging of the neighborhood of a pixel, and then replacement of that value. But what this D does is to modulate that averaging by saying, okay, along this direction you can't average too much, but if you go left to right across pixels, then you can replace with the averages, and so that's how it prevents smoothing across edges. Because what this D is derived from the gradient of the image. Actually, they are from the gradient of image. So it actually has edge information, and edge information is what is used to modulate the smoothing, right? So the homogeneous diffusion, which we talked about, which is equivalent to just doing Gaussian smoothing, is independent of the strength and direction of the gradient, right? It's just some constant value. Okay, so D is basically in this case 1. So, for instance, if you're looking at two directions, right, then D will be a 2 cross 2 matrix. So, D of xy in the case of homogeneous diffusion will just be some constant times your identity matrix. Okay, this is homogeneous. In the sense, it's the same across all directions, right? On the other hand, inhomogeneous diffusion, it depends on the strength, gradient strength. Okay. And so it's basically some function of the gradient, and so we can write in the case of inhomogeneous diffusion, we can write D of xy as some epsilon, some function of the gradient of your image. Okay, usually it's squared. So it's the same here, some function of gradient of u squared. Again, this becomes 0, 0. Once again, there is so it is in this case what we are looking at is the magnitude of the gradient and not at the direction, right? So a typical function, this epsilon, is basically a function which is epsilon naught some lambda square by gradient of u squared, in this case it's a norm, plus lambda squared. Okay, this is some function. So what it does is, so if this is basically your diffusion coefficient, right? So diffusion coefficient is very low when gradient is very high, right? That's what this formula tells you. Now, where is the gradient very high? Gradient is very high at the edges. This denominator is high at the edges. So pretty much at those points, this epsilon goes to 0. So there is hardly any diffusion, okay, across edges. But then it is allowed. Okay. So if you have very large lambda, then this gradient of u doesn't matter, right? So it just becomes epsilon naught. Okay. So the degree of this inhomogeneity depends on lambda. Okay. So, but this so-called tensor that we have here for D, it's still a diagonal, right? So it is no constraint based on the direction of gradient of u, right? So because gradient of u is a vector, so there is no constraint based on gradient of u. Okay. So let's say for anisotropic diffusion, where the diffusion is defined, this D is again defined at every point in the image, every pixel in the image. And for anisotropic diffusion, the gradient, the diffusion coefficient is such that in the gradient direction, along the edges, right, which you can get from the gradient direction, there is a diffusion is fine, while a diffusion perpendicular to the gradient is not in the sense direction along the edges. Sorry, let me repeat this. Along the edges, it's allowed. Diffusion is allowed, and perpendicular to the edges, diffusion is not allowed. Okay. So the gradient which you calculate in the image, correct, is basically perpendicular to the edges, and so along that direction there is no diffusion, while perpendicular to the gradient, which is along the edge, there is diffusion. Okay. So what typically people do here is to do the so-called eigenvalue decomposition of D. And then from there you can find out the direction of the largest eigenvector, and then you do the diffusion along that direction. However, so we can write down a formulation for that, but right now we'll hold off on that particular aspect. So what all we can say is that D is defined to be a tensor. And for anisotropic diffusion, we calculate the directions along which where diffusion coefficients are low and direction along which diffusion coefficients are high, and we solve the diffusion equation appropriately. Okay. So this diffusion, but we keep saying, right, what is it that we have to solve? It involves solving a PDE or a differential equation. And so the form of the PDE, let me write that down. In this case, when I said the differential equation, we have to solve it iteratively. Okay. So how are you going to solve that? So we are going to say, let me add this. I'm going to say that this U of x, y, t of I plus 1 is some U of x comma y comma t of I. This is iterative solution plus delta t times delta u of delta t. Again, u is a function of x, y and ti. And we saw that u at x comma y comma 0 is your image, input image. Okay. But what is delta u by delta t? This delta u by delta t is nothing but your divergence of your flux that I showed you earlier, j of x comma y comma t, and this divergence of your flux which we saw here, is nothing but which is equal to del dot d of x comma y gradient of u. So du by delta. So this equation delta u by delta t, this is what you solve with appropriately chosen d, capital D. Okay. So given this, we can go ahead and solve this. So there are many ways where we can bring this out. So for instance, even though this is spatially varying, this equation can be made linear or non-linear by how you compute d. So for instance, the most general form, d is computed from u at every iteration. You can also compute d from f, so it doesn't change every iteration. Okay, so both are possible. Once again, how many iterations do you have to do? That depends on the type of your problem, some of the parameters in the diffusion equation, etc. Okay, so we look at this if time permitting in more detail. So, but just to give an understanding, so everything depends on how you choose d. Okay, so you choose d to be a tensor which has preferential directions, then you get anisotropic diffusion, wherein you get smoothing along the edges, but not perpendicular to it, because d depends on the gradient, right? And if you choose d to be some constant, then it averages across everything. But you can choose d to be proportional to the magnitude of the gradient alone, but not worry about the direction. Then you get inhomogeneous diffusion. There is some smoothing of the edges, but not as much. Okay, so this is one of the techniques that was often used for quite some time, still in use. It requires a lot of fine tuning, but works very well because it comes from sound principles. Okay, so the next topic is bilateral filtering. Okay, so here this anisotropic diffusion filter and adaptive smoothing They are iterative, and this I haven't talked about, which will exclude this topic. But our smoothing are iterative procedures, right? So, but bilateral filtering does it in one step. Okay, and what it does is basically some weighted averaging, but the weighting factor takes into account similarities of neighborhood. So, what do you mean by similarity of neighborhood? So, when we saw that, remember I told you when we do this boxcar averaging, we can, for the weighting in the boxcar averaging, all the pixels in the neighborhood are weighted the same. But then you can put a Gaussian weighting on the neighborhood of pixels. But then that Gaussian weighting seems to be like a function of distance, correct? So you have a center pixel. As you move away from the pixel, the neighborhood's influence reduces. So you kind of made sure that you took that into account, right? But here there are two things. One is not only the distance from the center pixel, but also the similarity in terms of the pixel intensities themselves, right? So when here also it's weighted averaging only, except that you average pixels that are similar rather than pixels that are dissimilar. So for instance, I'll give you an example. Let's say you take a picture of a person, right? A face image, right? Now, if we want to average inside the eyes, the iris, etc., you would like to consider pixels in the other eye, right? Wherein all you would expect them to be similar to this the pixels in the two eyes to be similar. So, given this scenario, you would like to choose pixels in neighborhoods which are similar in pixel intensities, right? Not just distance. Okay. So that actually improves the outcome from this filters quite a bit. And bilateral filter is again a very often used filter, and it's one of the and there is some problems with in terms of execution time, but it actually does quite well. Okay, just quickly look at the formulation, right? So the first level of formulation is basically, this is what you have seen, is you have a Gaussian weighting. So if you want to, let's say it's like a 3x3 neighborhood, let's say we want to replace this pixel with a weighted average of the neighbors, right? So that's basically at so if you consider a neighborhood of ij, right? So x1 is the pixel you want, like here, and x2 basically represents locations which are neighbors of x1, which is basically the other pixel locations. Right here, right? This is x2. The red ones are x2. So you take the function values there, f of x2s, and then you have a weighting function. And what is that weighting function? The weighting function is nothing but it depends on the distance between x1 and x2. Okay, which is what I've, so which is if you subtract out the components, corresponding components, in this case there are two components for x1, two components for x2, right? You have a, let's say x1 is I comma j, x2 is m comma n, right? So you have that. So this is just a pixel index distance, and then you convert that into a weight by plugging it in here, right? So this dp of x1 and x2 is WSDP. So you calculate the distance between two pixels, that's your x in this case, and then you plug it in this formula, so you get exponential weighting. So this is one level of filtering. This is very similar to boxcar averaging, where in this case all the weights are 1, but in our case, we just have an exponential weighting. Okay. What is the other version of the same thing is, if you further weight it with, not with the what you call the WR here. I don't know, hope you can see this. I'll zoom this in. Usually yes. So you can see that. So the WS, we saw this we saw till now. You just add, on top of this you also add a other filtering thing, which is basically the same weighting, except that now it's the distance between pixel intensity. So you look at neighborhoods. So you can look at average of neighborhoods and see which one which is similar, right? So here you predefine the length of the neighborhood. That's how you would calculate it. Now you can see that this neighborhood is how you define it, correct? So you can choose pixel from very large neighborhoods. Not only are they weighted by distance, so if you go farther away from your center pixel, obviously the influence of that neighborhood goes down, but you can always see that, okay, I'm far away, but it's very similar. That's what this tells you. So I might be far away from my center pixel, but it looks like the neighborhood there is very similar to this neighborhood, right? That is what you get from this other weighting function, correct? So these two are, what you call weighting function is what the play between them is what gets you a better averaging. So eventually what you are doing is averaging pixels. Initially you are averaging pixels close by, in the assumption that in a very small neighborhood of the center pixel, pixels around it should be similar, right? So let's say I was giving you an example. You are looking at a blue sky, and if you take a small neighborhood in that picture of a blue sky, it will all be blue. It can't be anything. Some random purple color can't come up. Okay, maybe there are some exotic times when that happens, but mostly that's true, right? So the locally constant assumption is true there. Here, not only do you not assume that that's true, but you also say that there is redundancy in the picture, right? So you can, for instance, take a picture of some rolling fields, right? Rolling fields might have some greenery, some water bodies, etc., and then some more greenery. So there are all these green patches everywhere in that picture of nature, and they are all very similar objects, right? All let's say grasses are green. So then it's okay to average pixels from those areas also, and that's what this intensity weighting does for you. Okay, so there are various modifications to this. As you can see, this is a very computationally intensive process, right? So for every, you can take to the extreme by considering for every pixel, you can consider the entire picture, or you can consider like sampled areas in the image. All kinds of things you can do, and that will increase the computation time. So that's one of the initial criticism, that it takes too long, but it gives you exceptional results. But there have been quite a few innovations in this field, and people have figured out how to do this fast. We will not look at those algorithms, but just to give you information about that. So bilateral filters, once again, open source implementations are available. I urge for you to try them out. I will show them in a later lecture, a demonstration of bilateral filtering on images. You can add noise and then do the filtering. So in case you're wondering how do I know whether it's working or not, you take a perfectly nice picture, you add noise to it, and then do bilateral filter, see if it removes it. Okay, so that's the end to our filtering in terms of all these these kind of methods for noise removal. So we will, in the next lecture we'll look at the Bayesian estimation. Just again a brief introduction there, because the problem by itself is very complicated, but just to give you an understanding of how that problem evolved. Thank you.